Hey folks, this is the first of two short videos on graphing polar functions. And the first one, which is this one, is going to concentrate. I'll do an example of a cardioid and one of a limacon. And the second one will be devoted to polar roses. Okay. Uh, please do the exercises on that self-directed graphing worksheet that's on Blackboard. The solutions are all up there. It's good practice. Okay, so this first example I'm going to do is r equals 1 plus 2 cosine theta. And remember that in polar coordinates, what we try to do is we try to write r as a function of theta. Now, there are basically two approaches that we can take, and I'm going to sort of explore both. The first approach is a little more mindless. It's doing it on the calculator. So let me talk about that first. But I think as humans, and not just point plotters, I think it's good to understand why the functions look how they do. And also, important thing is by understanding a little more about sine and cosine, we can really answer some better questions and do it more quickly if we use our common sense and our mathematical knowledge. All right, so let's start with the calculator. Step one, I'm using a TAE 384 type machine. Step one, you turn it on. Step two, you want to be in degree mode. So set your machine for that. You also want to be in polar mode, and I recommend dot mode. We can always change to connected mode later. That's not a problem. And but I think the dot mode shows some interesting features as well. And then we go to the where is it? Okay, we then go to the window key, and theta min is 0, theta max is 360, and theta step, we're going to go in steps of 15 degrees. So we're only going to get a few dots, but I think that that's going to be helpful for this first introduction, and we can change it later on to 5 degrees or 4 degrees or whatever you want. But by making it 15 degrees, then we sort of guarantee that we hit all the angles that we sort of know about, like 30, 45. We'll also hit 60, 90, and all the quadrantal angles. So that's the idea. Okay. As far as x min, x max, we're going to go -3 to +3 x on the x's, and y min, y max also -3 to +3. And I'll try to select functions that functions. I'll try to select polar curves which live within that region. And what we're going to be looking at is we're going to be looking at the where the curve starts, where it ends, the direction it's traversed, and that kind of stuff will be important later on when we do parametric equations as well. And something that's normally done only in calculus is where we're going to look for maxes and mins. So it's what values of theta make R max, what values of theta make R min. And another thing that's also done pretty much in calculus, but we can do it here, is at what angle does the curve go through the pole? The pole, of course, is the same as the origin in XY coordinates. Okay, so I've only picked two problems to do. They're going to be fairly quick. Oh, another thing, if you're doing it by calculator, what you should do, what's important is you can also go to table set. And if you do that, you can start the table at 0 degrees and have an increment of 15. And then you can press second graph, which is the table, and you can actually see values. Okay. Another thing that we'll do is we'll do a trace on the curve. If you're working with the calculator, I'm not going to do it on the blackboard here, but for your understanding, it might be good to do. So you can go into second format and select rectangular GC, rectangular grid coordinates. That'll just help you understand a little bit better. Okay, so here we go. And what I've chosen to do here is I've chosen to do, as the first one, r equals 1 plus 2 cosine theta. And even though I'm doing it in degrees, we can also understand, you should be able to understand that you can make a change into radians. All right, so we go 0 degrees, 90, 180, 270. which is 0 or 2 pi radians, pi over 2 radians, pi radians, 3 pi over 2. And just as a general bit of understanding, we're working on cardioids and limacons. This is the general form. R equals A plus or minus B, either sine or cosine, okay? And typically, notice I got the plus or minus here, so we're always going to think of A and B as positive, all right? And it turns out you get a cardioid. Cardioid means heart. You get a heart-shaped region. If A is greater than B, of course, they're both equal to 0. And you get a dimple, which is like a cardioid, but it's a little less pronounced. It's going to look like this. So with a cardioid, if A is greater than or equal to B, then we get a dimple, in other words, no loop, a limacon, alpha loop, right? You get a loop. In that case, B is greater than A. Okay, so let's start with number 1. And looking at A and B, in this case, A is 1, B is 2, B is greater than, so we expect a limacon, we expect a loop. Okay, so let's actually do this then. And what we're going to do is, I guess I'll use green. Let's see how green works. Is that going to work? Yeah, that looks pretty good. Okay, so what we're going to do is we're going to think of the cosine curve here. And cosine starts high and ends high, bottoms out in the middle. I just have it set up in degrees, but you could think in radians as well. Okay, so when theta is 0, cosine is 1. So this is going to be 1 plus 2 or 3. So that's going to plot a 0.3. So let's do the quadrantal angles first. 90 degrees, cosine is 0, so I'll get a 1. Okay, so let's see, if cosine is 0 at 90, this is 0, 1 plus 0 is 1, get that point. Okay, at 180, cosine is negative 1, 2 times negative 1 is negative 2, plus 1 is negative 1, so when I'm looking out at this direction, again, R value negative 1, which flips it back. We'll talk about that later. Okay, and when when theta value is 270, the cosine is 0, so we get another 1. And when we go back to 360 or 2 pi, you get a value of 3 again. Okay, so let's sort of fill in the things in between now. Okay, notice that cosine has a value of 1 at 0 at theta equals 0, and a value of 0 at pi over 2, or theta equals 90. And it's decreasing. So what's going to happen is the curve starts out a distance of 3. And notice these little circles here, radial, okay? And they appear on that worksheet, so that should help you out a little bit. So it's going to start at 3, and it's going to shrink down to 1 as we go from 0 to 90. And if I pick 60 degrees, cosine of 60 is a half. 2 times a half is 1, 1 on 1 is 2. So when I'm at 60, I'm going to be radially out about a distance of 2. So that gives me an idea that my curve is going to go something like this. Okay? And, okay, so now what happens now is cosine now becomes negative from 90 to 180. So as they go from here to here, the value of cosine is negative. Okay? In fact, the cosine of 120 okay, you should know the cosine of 120 is negative a half. Okay, so I'm picking out this angle because something interesting happens at that point. Okay, so when I get negative a half here, this becomes a negative 1. 1 and negative 1 is 0. So at 120 degrees, the curve is there. And since it's decreasing, it's going to basically look like this. Okay, and then it's also negative here. It's a negative 1, and it grows. So what's going to happen is the curve is going to come in like this. And you can see that if you take a look at your table. Okay. Also notice whenever you have a cosine, it's pretty much going to be symmetric about the x-axis. It's an even function. Okay, so now when I look from 180 to 270, it's -1, but increasing. So the value of cosine, when I put this in here and add a 1, it's going to look like that. Okay, and when I get to 270 degrees, all right, the cosine of 270 is 0. I get back to a 1. So when I'm looking down here, it's a 1. Okay, and when I go from 270 to 360, what happens is cosine begins at 0 and it increases up to 1. So it's going to go back to 3. So it's going to be 1 and increasing more than 1, a little more than 1, so forth and so on. And going to look something like that. Okay, so it didn't come out all that well, but let's write down a couple of these points then. All right, so this is the point r comma theta. All right, so r would be 3, and theta would be 0. I'm going to put it in degrees, but we could put in radians. Now, we learned this is 2 comma 60 degrees. Okay, this point here would be, let's see, when did we hit a 1? That's a 0, so that would be 90. So this would be 1 comma 90 degrees. Okay, this point here, I know that you're going to say 0, 0, but actually it's not. It hits that place when the value of cosine is -1/2, right? Because that's when we get 1 plus 2 times -1/2. 1 plus -1 is 0, and that happens at 120. So this is going to be 0, 120 degrees. Okay, and it goes around in here, and this is kind of very, very curious. Okay, this is when theta, or the angle, is 180, and then you get a value of -1. So you get -1 comma 180. So r is -1, and the angle is 180. So don't forget the way that works in polar coordinates. If you go out like this is 180 degrees. A negative r flips it. So that's how come that's a -1 comma 180. Okay, and then it comes around again and it hits here a second time, and this time I believe that would be, let's see, I think it's a 240. Let's see if that's right. Okay. Okay, so this is 240. Okay, so we're looking for when is cosine again a -1/2 to make that a 0. Okay, so let's see, 240, this reference angle is 60. Okay, so this would be 30, 1, 2, radical 3. And as you can see, the cosine of 240 is indeed -1/2. And if I put that in, -1/2, 2 times -1/2 is -1, 1 and 1 is 0. So this point also has coordinates 0, comma 240. Okay, and then it comes down here, and this of course would be the point 1 comma 270, right in there. And this point here would be 300 degrees. You can check this out. So it would be 2 comma 300, because you'd have another reference angle of 60, the cosine of that. Okay, so we could do that. Yeah, let's actually do that. So this would be 60 in here. This is 300 degrees. Okay, so this would be 30. So 1, 2, radical 3. Let's get the signs right. That would be negative, of course. So the cosine, is that right? 60, 240, 60, 300. I'm doing wrong here. 60, 31, 2, radical 3. let me look at that again later. Okay, so this might be 330, 60, 300. Okay, I'll look at that again later. But okay, so that would be a two. Oh no, this is correct because the cosine here is positive half as I had in my diagram. 2 times a half is 1. 1 and 1 is 2. So that's is correct. Okay. So now, if you want to get a little fancier, you could say, all right, the curve starts here. It's traversed in this direction. Okay. And it comes back, continues through, and it ends there. Okay, so let's talk about this a little bit. A couple things that are a little strange about polar. This point has several representations on the curve. It's 0, 120, or 2 pi over 3. And this is 0, 4 pi over 3. The same point has different representations. So if I ask you, is 0, 0 on this limacon, the answer is no. This point is on the limacon, and this point is on the limacon, but 0, 0 would imply that when theta is 0, r is 0, and that's just not true. Okay, so you have to be a little bit careful. It looks like what we would call 0, 0 in rectangular coordinates, but that point is not on this curve. Okay, so kind of strange. Okay, so let me make some room here. And other things that you should understand. And you know, like I said, you would do this on the calculator. You can see it in slow motion. You can actually see the dots. Okay, you get a little better idea of how it's working. Okay, so let's talk about R max and R min. Okay. Maximum R, the greatest value of R is when cosine is its greatest value. In this case, when cosine is a 1, and that occurs at 0. So we have maximum R when, no, maximum R. R is a positive 3 when theta equals 0 radians or degrees. So that's the greatest R is, okay? And the least R is when this is going to be least, and this is going to be least when cosine negative is the most negative. Cosine theta is the most negative, so that will be at 180. So we have our minimum R, and that R would be, as we can see, a -1. Kind of strange, you think that that's a minimum, but it is, when theta equals 180 degrees or pi radians. Okay, so that's pretty much all I wanted to do with that example. And notice this is a limacon because it has a loop, and the size of the loop is determined on the relative size here. If this were a 3, let's say, then this could have a value of -2, right? When theta is a 180. So the size of the loop is dependent upon that relationship. But as long as B is greater than A, you're going to get a loop. The word limacon starts with loop, the word L starts with loop, and that's a good way of remembering it. So now what I'm going to do is I'm going to do the second and last one, which is a cardioid. So a cardioid is not going to have a loop. Instead, it'll have a little dimple. And if A equals B, okay, it turns out it actually looks like a heart. Okay, and that's why it's called a cardioid. So let me redo this. Unfortunately, it's going to take a few moments. So in between, at any time on this video, if you want, you could always pause it. You can rewind. You can look at the diagram a little more carefully. It's a little hard to do on the blackboard, but okay. So here we go. The one I want to do now, this is example number 2, would be R equals 2 minus 2 sine theta. Okay, now here's a situation where A and B are equal. And don't forget, we're not really looking at the SIGN here, right? They're equal. So we're expected to get a cardioid type picture. Also, since this is a sine curve, it's going to be symmetric about what we would call the y-axis or the pi over 2 axis. And since this is a negative, we expect it to be the negative of the lower part of that. Okay, so to help us out, let's draw a general picture of the sine curve. Okay, so this would be your 180, the 270, 360, 90, and 0, of course, and 1, and -1. And so this would be a rough, very rough sketch, you can tell. Fix it a little bit, maybe, of sine theta. Okay, so let's go ahead and let's take a look at this. And in order to do this, I'm going to need to make a grid. That's not very good. So let me see if I can take a little bit longer, but okay. All right, so 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, and of course you have 0 degrees. Let me shorten that up a little bit, make some more room here. You have 0 degrees, 90, 180, and 270. Okay, so here we go. First of all, now again, since this is a sine type, we know from experience, hopefully, that it's going to be symmetric about the y-axis or the pi over 2 or the 90-degree axis. Okay, so we start out with 0, okay, at angle of 0, right? 2 times 0 is 0, so we plot this point. So this would be the point 0, comma 2, and don't forget it's r, comma theta. Okay, so when, whoops, that's not correct. Let me fix this up a little bit. When theta is 0, r equals 2. Okay, so that would be the point that. Now, here's what's happening. The sine curve is increasing. At 90, it hits a high maximum of 1. So at 90, this is going to be a 1. So 2 minus 2 is 0. So this would be the point 0, comma 90 degrees, or pi over 2. And don't forget, we're using r, comma theta. Okay, so this is the r, this is the theta. Okay, so what will happen here is if we go to our table of values, we'll find, well, we know that when sine is 30 degrees, it has a value of 1/2, right? So let's just go over that again. When sine is 30 degrees, you get 1, 2, radical 3. Sine is opposite of hypotenuse, it's a 1/2. So 2 times a half is 1. 2 minus 1 is 1. So we're 30 degrees. We're radially out 1 unit. Okay, so this would be the point 1, comma 30 degrees. So what's happening is our curve is going to start looking like that. Okay, I didn't draw that very well, but you know, it's what happens. Okay, now same thing happens here. At 180 degrees, sine 180 is 0. So at 180 degrees, we're at a 2. So this would be 2, comma 180. And in between, the same type of thing is going to happen. So the curve starts out going like this. It hits here, and it's going to now, when this reference angle is 30 degrees, which would be 150. I don't have really room to put it in. It's going to be a 1/2. 2 minus a half is 1. So we're going to get a picture that looks a little bit like this. Okay? Okay. And what happens is, let's look at our 270 now. We'll sort of fill in between. At 270, sine is a -1. And if I put a -1 in here, right, I get 2 minus 2 times -1. I end up with a 4. So that means that when I come around here at 270, it's going to be a distance of 4. So this will be 4. Let me put it in a place where it's not going to interfere. 4, comma, 270 degrees. Okay? So let's look at another angle. Let's look now at 210. All right? So you probably wondered, why am I looking at 210? Well, let's see. Okay, so this is 210 degrees. This reference angle would be 30. So once again, you have 1, 2, right, 3. And at this point, at 210, the value of sine is -1/2. And if I put a -1/2 in here, right, it's going to look like this. This is a 1, 2 and 1 is 3. So when I'm out at an angle of 210, I'm going to be radially out 3 units. Okay, so what's going to happen? You can plot some other points here, and what's going to happen is the curve is going to come down like this. Okay, and now coming around, let's look at the next time when sine is going to be a convenient value. So let's say we're looking at 330. Okay, so you're looking at 3. Now, let me make this a little bit bigger. Yeah, because I can't much. Coming around here, we have 330 degrees, reference angle of 30. And again, 1, 2, radical 3, but this is a negative. So at this point, at this place, 330 degrees, looking out in this direction, okay, I'm going to have a sine which is -1/2. So I'm thinking of my radial line there, okay, okay. And if I put a -1/2 in here again, I'm going to get a value of 3. So that means at 330, I'm going out about 3. Okay, and if I can continue with our plot, I will end up with I guess a broken heart. Haha, that's a joke, but that's my cardioid. Okay, so notice a cardioid, it looks like a heart, and I chose this form of it for the simple reason that it actually looks a little more like a heart. And if I had a plus here, of course, it would look a little like this, okay, which is an upside down heart. So that's the reason why I did not want to choose a plus. I chose a minus. So you can see it's symmetric about the 90-degree axis. We call this the y-axis, and also it's pretty ugly, really. And also, oh, that's worse. And also, it is the -1/2 of the y or the pi over 2 axis, because that's a negative. Okay, so let's answer some of the other questions about it. And let me continue to put in these little arrowheads to show the actual flow. And you can see this on your calculator. You do it in dot mode, you press trace, and if you want to see it a little bit better, you put in connected mode, you press trace, and you can see how it goes around in that direction. Okay, so the other, let me label this point. This would be 3, 330 degrees. And again, if you're doing this in radian measure, I guess this is 11 pi over 12. No. Let's see, 330. So this would be 11 times pi over 6. So it's 11 pi over 6. So if you had this in radian measure, it would look like that. It's the same point. Okay. All right, so let's look at R maximum, or let's look at, yeah, R maximum. Okay, R is the greatest when, well, let's see, when this is a 4. And when is that a 4? That's a 4 at 270 degrees. So R is a 4, and theta is 270, or of course 3 pi over 2. All right, and you can see that because when sine theta is a -1, this is a 4, and sine theta is a -1 at 270. So that's when R is the greatest. Okay, R is the least. We call in mathematics a minimum. Well, let's see. Um, it's going to be a minimum value when this is a 0. Well, no, that's not true. It's going to be a minimum value when the whole thing is 0 in this case, but when a sine theta is a 1, then we're taking away the greatest amount, right? And then you'd have a value 0. So R would be a 0 when theta equals, well, we're taking away the most when sine theta is a 1. That would be at 90 degrees, or we could say pi over 2 radians. Okay, so there are a variety of problems for you to do in a self-directed exercises, and you can look at things like the direction. You can label points. You can look for mins and maxes. You can look at symmetry, give you an idea that this curve, of course, is symmetric about the pi over 2 axis, whereas the first one we did was symmetric about the x, or the polar axis. And these are all things that you can tell from looking at the curve. Now, any analysis that we did, you notice I didn't have my hands on the calculator, you can go ahead and you can take a look at the table on the calculator and you can trace, and that's going to add to your understanding of what this will look like. Okay, so what I'm going to do next time, I'm going to do polar roses, and hopefully my graphing technique will get a little bit better. But limacons and cardioids are very common polar curves. Okay, so see you in the next video.